Hello, I have explained a lot about why we have to use the quantile regression, but like the mean regression is still good. Mean regression is more popular, so there are many advantages of using the mean regression. Let me list some of them. First, it is easy to calculate. In the mean regression, there is a closed form solution, x prime x inverse x prime y. So it's really easy to calculate, but the quantile regression does not have that kind of simple solution. So every time you estimate a quantile regression, you have to solve out the maximization problem or the minimization problem. That is a computational cost, quite a burden. That's why the quantile regression was not popular in the past, because computer was not good enough. But these days, it's not a big problem. Actually, estimating a quantile regression is not it can be done in a second in your desktop. So don't worry about the computational problem now. And second, technically, theoretically, quantile regression involves non-smooth, non-differentiable functions. So the Taylor expansion approach does not work, and theory becomes more complicated. Also, it is not your concern because econometricians already solved out the the problem, and anyhow, you are not going to study the theory if you are not going to major in econometric theory. This is not your problem. Uh, all the programs there are programs written so that the quantile regression is easily handled in a similar way to the mean regression, so it's not a problem. 3. Quantile operator is not linear. I will explain this in more detail later. So the mean is easy to handle. We know a lot of nice properties. For example, the expectation of x plus expectation of y equals to the expectation of x plus y. It is not true for quantile. So quantile is not easy to handle, and it it may be a small difference, but actually in the proofs, like in the earlier chapters, we have used the properties of the expectation in many places. For example, when we study partition regression, two-stage least squares, we used this property x plus y expectation equals to expectation x plus expectation y. That means the quantile regression has no theory like this. Two-stage least squares uh, do not work for the quantile regression. So it makes the quantile regression more complicated. Another reason, endogeneity. Endogeneity is continued to this. Endogeneity causes a very complicated problem for quantile regression. That means, more technically speaking, you are minimizing something, but the criterion function is non-differentiable, non-smooth. Okay, that is okay, but at the same time, it is not convex. It may be it is not smooth and not convex, so minimization problem can be very unstable or may converge numerically, may be very different. So that's a different problem. And number 5, discrete outcome, the binary dependent variable does not work well with quantile regression. So quantile regression is not used for discrete dependent variable models. That is, so these are the reasons why the quantile regression cannot completely replace the mean. The mean regression is useful, still useful in these cases. So um, do not abandon the mean regression. Now I'm going to have some notation, setup notation, and I will explain some basic properties. So first, suppose that capital F subscript y is the cumulative distribution function of a random variable y, and y is a scalar variable. If it is not scalar, the quantile is not well defined. Quantile is defined for a single one-dimensional random variable only. Then definition, it is the definition of distribution function. And for a specific tau between 0 and 1, we will define quantile, tau's quantile of y as the inverse function of the functional form, the distribution function. So mathematically speaking, it equals to this. This is infimum. You don't need to, in case if you don't understand what it is, you don't need to worry about that. Simply speaking, it's an inverse. So if this is true, then tau's quantile is lowercase y. That will, so we are considering this definition in case the distribution function is not continuous. If it is not continuous, then definition requires a little bit more details, and it's not a big concern. If the distribution function is strictly increasing and continuous, then it's simple inverse function. Okay, we'll ignore that. Conditional distribution is similar. So it is conditional distribution function defined in this way, and then conditional quantile, conditional tau's quantile of y is the inverse of this. So when I write it this way, inverse function of this is argument is only at this point. X is fixed, but its argument is the inverse is taken with respect to this argument. This is the mathematical notation we usually use. And then and also if the conditional distribution function is strictly increasing and continuous, infimum does not matter. It's simply inverse. So you don't need to worry about that. And in the regression model, we will assume that the conditional quantile is a linear function, which means this in terms of probability. They are equivalent. This is exactly the extended definition of this, right? Think about this. Or equivalent, earlier I explained this. In the regression equation, you may impose this or this. So simply, this is intuitive. You are replacing expectation with quantile. So quantile equals to 0. So the conditional quantile of epsilon given x equals to 0, which replaces the conditional mean independence. If you change the quantile into probability using the definition, you get this. So change tau and 0. Then you will get the same result. And let me explain some basic properties of quantile function. First, if tau increases, obviously quantile increases. Say 10 percentile must be smaller than 20 percentile, and say 90 percentile must be greater than 80 percentile. It is monotone if the distribution function is strictly increasing. So it is pretty obvious. And therefore, here comes another problem. In the linear regression, by the nature of the linear function, two linear functions will cross at some point, unless they are parallel. So if they're parallel, they may not cross, but when their slopes are different, they will cross at some point. Then this monotonicity may be violated. The monotonicity may be violated at some point, which is a problem in quantile regression called quantile crossing. So there is no direct solution. If the crossing happens outside the support of x, so there where we are not interested in, then it is not a big problem. But if the quantile crossing happens where you observe many samples, then linearity may be a problem. You have to think about your model again. So that causes a problem. And another nice property, another important property we are going to use a lot is the invariance to monotone transformation. So think about this. Say g is a function, weakly increasing function, and y is the variable we already know, and we define a new random variable after taking this transformation. So a is a transformation of y, a new random variable. And if you know, and suppose that you know the quantile function of y, then can we infer about the quantile of a? The answer is yes. The answer is given by this, right? So to show this, it's simple. The quantile satisfies this because we assumed strictly increasing distribution function. And then if you take g on both sides of this inequality, take g of y and g of q, and then place g here, and then you get this. This equals to tau, so this is exactly the definition of quantile. Tau quantile of A is given by this guy. So you show that, we just prove that this. This is when you have weakly increasing function, but if you have weakly decreasing function, it will go the other way. So tau quantile for A will be related to 1 minus tau quantile of Y because it's decreasing. So bottom 10% will become top 10% after taking decreasing transformation. So both are intuitive because it is ordering, it is ranking. So you are taking, the ranking does not change when you do a monotone transformation. This is useful in this example. Think about this. We consider this kind of model a lot. Log of y is a linear function of x with this assumption. And then quantile of log can be interpreted as log of quantile. So log of quantile is given by the linear function. So quantile of y can be written as exponential of the linear function. So compare this result to the mean regression case. Mean expectation of log is different from log of expectation. We actually have Jensen's inequality. One is strictly greater than the other. So this is a nice property of quantile regression. And in another example, censored regression model is another example of using the monotone transformation. Suppose that y star is a latent variable, underlying variable, y star, but it is not observed. You only observe y if it is positive or 0. So below 0 is not observed. A typical example is working hours. I would like to work negative hours, but it is not possible. Physically, it is not possible. Then you only observe. You can choose only 0. Anyhow, in this case, the observation can be written as a maximum function, which is weakly increasing, which is also weakly increasing. Then you may apply the same idea. So quantile of your observation can be interpreted as the quantile of the underlying variable, even if you do not observe the underlying variable. So it helps identification. So we would like to identify the distribution of the underlying variable, and which can be inferred by the observed variables. This does not work in the mean regression, like mean of max is different from max of mean. So the quantile regression is useful in this kind of setup. So that's okay. I will stop here. Thank you for watching. We'll continue on the next one. See you later.